Hello, everyone. I would like to welcome you all back to our Water Productivity Masterclass series. My name is Lauren Zielinski, and I work at IHE Delft on the WaterPIP project, and I'll be moderating the webinar today. And I'm also joined by Abraham Abhishek from Meta, who will be helping with the IT and technical part of the webinar. So I think we have some people who have introduced themselves already, but we're very excited to have you all here, and we would like you to say hello in the chat and just put your name, the institute or the organization where you work from, and the country, and it really helps us understand who we're engaging with and the different regions and different sectors of water from around the world. So thank you. If you're new, if this is your first week to the Masterclass series, it is brought to you by the WaterPIP project, which stands for Water Productivity Improvement in Practice. And it's a project that is funded by the Dutch Ministry of Foreign Affairs, bringing together organizations focused on water science and water management to improve water productivity in the agricultural sector. So the main organizations that are leading the activities are IHE Delft Institute for Water Education, Wageningen University and Research, and Meta. So you'll be seeing different people from these organizations on these webinars. And so I'd like to welcome you to week 3. So we're actually on part 2 of monitoring water productivity using WaPOR. Last week in part 1, we talked about what is the WaPOR portal, what are the different data that you can find on the portal, and how to do different analyses on that portal. But today we're going to be focusing on how to take that data and use it in a more advanced way using GIS and Python to get the specific information that you're looking for your projects. In the remaining 3 weeks, we'll be talking about water productivity and sugarcane production, so focusing on a specific crop and also looking at different scales, such as the river basin scale. The following week, we will discuss socioeconomic water productivity. So how can we look at water productivity from different viewpoints around social uses and economics? And then our last week, we will talk about monitoring water productivity using AquaCrop, which is another open source software focused on irrigation and crop analyses. And just a reminder, if you would like to rewatch any of these webinars or download the presentations, there's 2 locations you can go to. First is the WaterPIP project website, so that is waterpip.un-ihe.org. It's functional now, it's live, we're very excited, so you can go there and look at the different videos, download the presentations. If there were unanswered questions, we will be putting them on the website as well. And in the future, we'll have more resources available to look at different parts of water productivity, more reports, and things like that. So please visit our website frequently, and you can stay up to speed on those things. You can also go to the waterchannel.tv and go to their webinars page, and then you can see all the previous webinars from this series, including the videos and the presentations. So our agenda for today, we're going to start with a video from Vic Tran from IHE, and she will talk about how do you download the data using the WaPOR portal. That will be followed by Sajid Parith, also from IHE Delft, and he will talk about how to process the data from the WaPOR portal in QGIS. After that, Vic will talk about how to do bulk downloading using Python scripts. And then Abebe Chukala, also from IHE Delft, will take some time to talk about how to assess water productivity and other irrigation performance indicators using Python. And then after that, we will have a Q&A session where we can answer everyone's questions as a group. So like the previous weeks, we will not be taking breaks in between the presentations, but if you have a question, please put it in the chat box, and Abraham and I will be collecting the questions, and we will put it into the Q&A session at the end. So we encourage you to make comments and questions in the chat box during the whole time to stay engaged. And just as a quick note, today the presenters will give a short presentation, but then we'll be live sharing their screens, so using the different programs. We're going to make the screen a little bit bigger so you can see it better, but if you would like to zoom in to see really specific things, you can use the buttons on the top right-hand corner of this part of the screen, and you can zoom in on where the mouse is. And if you click all the way to the right where the options are, you can choose your zoom level. So depending on which view you would like, you have some options to see things better. So with that, I think we're going to start with the video from Vic, and she's going to go through step by step on how to download data using the WaPOR portal.
My name is Vic. I'm a member of Water Accounting Group at IHE Delft. In this video, I will show you how to download data using the WaPOR portal. I will now demonstrate how to download raster data from WaPOR portal. You can either download a whole layer data through the catalog or using the crop raster in the analysis. Let's first look at the catalog. In the catalog, you can select which level of WaPOR data you want to download. You can also filter by theme like water productivity, water, land, climate. For example, if I filter the data layer by climate theme, I will find reference evapotranspiration and precipitation data layers. When clicking at the data layer card, I will find a full description of the data, including unit, spatial resolution, spatial reference system, and conversion factor. Here you can filter the dataset by year or month. For example, here I want to collect data for October 2009. Then I will just have to click on download button. Then I will be downloading the reference evapotranspiration data for the whole WaPOR region. Since the conversion factor of reference evapotranspiration layer is 0.1, we will need to correct the downloaded raster with this value. I will open the downloaded raster in QGIS. Then we will raster calculator to multiply the raster data with 0.1. Then we will have the corrected raster. And here we have the unit in millimeter per month. Back to the catalog. For the level 2 national 100 meter, you can also filter the raster by countries and by water basins. Similarly, for the subnational 30 meter level, we will need to select the area with available data. Notice that with the catalog, you will download the raster data for the whole WaPOR region or whole country or water basin. So in case you want to just download, for example, a very small area, you will need to use the analysis tool. Before that, we need to select the layers that we want to clip raster. For example, here we have gross biomass water productivity. I will select to download net biomass water productivity. And you can select the time also. Always check the legends if you are selecting the right layers. And now we click on analysis. In the operation, you need to select area raster download. Here you click on select area. You can choose one of the saved area in your WaPOR or draw a new one or upload a shapefile. So let's draw a new one. Here I want to collect data for the office Tunisia in Mali. Let's, for example, draw a simple shape around this area. Then I will save this for later use. click Run Operation. Once it's completed, I can click on the green button to download. Now I will open this cropped raster in QGIS. Now I will zoom in these layers and hide the other layers. Now don't forget that all WaPOR layers will have a conversion factor, so we go back to the catalog and check the net biomass water productivity information. So here we find that the conversion factor is 0.001. So now I'll go back to QGIS, and similarly I can use the raster calculator to multiply with the conversion factor. And then I can save this as corrected raster with the unit is kilogram per cubic meter. And this is the end of the demonstration. Thank you for watching.
Thanks, Vic, for that video. I think it's quite helpful to see how to do all the downloading procedures on the WaPOR portal, because we will need them to do the analyses in QGIS. So now Sajid Parith, he will present more on how to do this in QGIS.
Hello everyone. I hope you can all hear me well. So I will continue from where Vic stopped. I will continue to show you how to process WaPOR data which we have downloaded for a particular study area, and how to process that data to compute some of the performance indicators in QGIS. So here is a study area which I think my following presentations, we will all focus on this particular study area. This is the sugarcane scheme at Sinawane in Mozambique. And the season which we are going to consider is 12 months from September 2018 to October 2019. In this particular session, I will focus only on one season in 1 year, which is 2018-19, the crop season. I'll be mainly showing three WaPOR data, three variables from WaPOR, which is ETA, actually WaPOR transpiration, and reference ET. And all the data sets which I'm going to show you is decadal. So one of the time frame which WaPOR offer is 10 days data sets. They call it as decadal data sets. So for a year, there will be 36 maps. So if you download for a particular year, for example, 2009, you can see that there are 36 maps. And on the right side, you will see 2018-19 maps, which I will be using here, which cover the entire season. So because the season covers 1 year, it has 36 maps as well. But it starts from 2018 October to 2019 September. So what I'm going to show you is to compute irrigation performance indicators in QGIS, which Abebe will, in the following session, will explain it further, how to do that for all the years using Python. Here I will show you 1 year. I will show you how to compute these indicators. And this is the workflow. We have 3 variables, actually WaPOR transpiration, reference ET, and transpiration. First, we have to do a seasonal aggregation to get seasonal maps. We have to mask to study area. And then from the masked seasonal maps, we will compute those indicators. So without wasting much further time, let us get into QGIS. Can I share the screen? So I'm going to share my screen to show you the process in QGIS. Okay, I hope you all are seeing my screen now. Okay.
Yes.
So as you can see, this for me here the QGIS is open. I have a background map, and you can see Xinawane, which is the sugarcane scheme. The boundary of Xinawane also open here. Now I will show you first how to compute seasonal maps. So let's compute seasonal actual evapotranspiration from the data downloaded from WaPOR. Just keep in mind that all the data which have downloaded in WaPOR is already clipped to this rectangle, and also the conversion factor is already applied, as Vic just mentioned in the previous video. So to do a seasonal map, let me just start from the beginning. I always go to processing toolbox, where you get all the modules available for raster and vector processing. I will use a module called r.series, which can be used to aggregate a list of raster maps based on different functions. So what we need to do is we have to add all the maps, all the decadal maps in that particular year to get the seasonal map. So I'll go to the folder, add files. So as you can see, I have already arranged it. So actually evapotranspiration 36 maps. These are the 36 maps covering that particular year. I will add them here. And you can see that 36 maps are selected. And the aggregate operation, I will select. There are many operations available, but in sort of average, what I need is sum, because we need to sum all those maps. So I will select that one, and you can keep all other defaults, and you can save this file and give a sensible name. I'm giving it a name called seasonal ET.
Oh, looks like maybe Sajid dropped out for a moment, but hopefully he can join us again in a few minutes to finish his presentation. But in the meantime, maybe we see him again.
Yeah. Can you hear me now?
Yes, welcome back.
Yeah. Sorry, I was lost again. I'm using connected internet, but still. Okay, can you see the screen again?
Yeah.
Okay, so you can see that the r.series is finished. So the map is open in the map view. Now the next step is to clip this particular raster layer based on the shapefile which is open here, Xinawane. So for that, I will go back to processing toolbox. I will search for clip, and I can see there is a module called clip raster by mask layer. I will select the input layer as seasonal ETA, mask layer as Xinawane shapefile. I will select the source and target CRS, both are same, so even if you don't select it, it should work. And then I will save this file as clip underscore clip, and I will run it. It'll be very quick. And you can see that I have seasonal ETA already prepared here. I will remove the other one. So similarly, I have computed clipped seasonal transpiration and reference ET maps. So I will, you can follow the same steps later on, but I will open them again. I will open them which I have already prepared earlier. So I have the seasonal ETA, seasonal transpiration, and seasonal RET here. Let's give some color quickly to the transpiration. see, I'm giving some random color scheme here. So this is how transpiration looks like. Now coming back to my presentation, here you can see the first indicator which we need to prepare is equity. And equity is coefficient of variation of the seasonal ETA over the entire study area. Here it's safe for us because the entire study area is one crop, which is sugarcane, and it's already clipped to that boundary. So we assume that there is no mixed crops here, and it's true for in the case of Sinawana, it's sugarcane. So let's compute the CV, coefficient of variation, and to do that, I will use a module called r.univar. Univar computes univariate statistics of a particular raster map, and I will open it. I will select the seasonal ETA, and for another indicator which is coming following this particular indicator, we also have to compute the percentile, 99 percentile. So I'm also computing 99 percentile here. I will use comma as a separator, and then I will save the univariate results into a text file and run it. So as we use the comma as a separator, it can be opened as a comma separated file. And I have already opened it here, and you can see that it computes a lot of statistics. And one of the statistics is coefficient of variance, which is 13.8. So that is, you can consider as equity. And you can also see that it has computed 99 percentile here, which we will use later. The next indicator which we are interested is beneficial fraction. It is kind of easy to compute. It's seasonal transpiration divided by seasonal evapotranspiration. So as Big showed earlier, we will go to raster calculator. I will set an output layer first, and I will use this name. I will call it BF 2019 clear. And what is the equation is TA divided by ETA. And it should give me the beneficial fraction. We can also give it a nice color, and it will give you much more information. So this is a beneficial fraction map for 2018-19 crop year. Now let us do the next indicator, which is adequacy. For adequacy, we need potential ET. So the equation we use is actual evapotranspiration divided by potential ET. And the potential ET is calculated by multiplying seasonal reference ET by Kc. And the Kc value which we are using here is 1.045 for sugarcane. So what we need to do is we'll go to the calculator again, compute seasonal ETP, then select reference ET, multiply by 1.05. That will give you ETP. ETP is there. Then let us do, so as I said, adequacy is ETA by ETP. So now let's select ETA divided by ETP, which will give you the adequacy map. In this case, maybe you are interested in the univariate statistics, so you can quickly do statistics here, raster layer statistics, select adequacy, just run it. It will give you minimum, maximum, and the mean value. Maybe the mean adequacy value is more meaningful here, which is 0.63. Now let's come to the last one, which is relative water deficit, which is 1 minus ETA by ETX. So I have already shown you how to compute 99 percentile, because in this case, the maximum crop ET we compute as 99 percentile of the seasonal ETA. It's one way of doing it. And I've already shown you using r.univar how to compute different percentiles. There was a question in one of the last webinars. So that is already there in our in our statistics table 1644.27 millimeter per season. So we will use that value to compute RWD. So we will go back to raster calculator again. I will give it a name, RWD 2019 clip. And I will use the expression 1 minus, open the bracket, just clarify this TTA divided by, what is the 99 personnel, 1644.27, 1644.27, close the bracket, that's it. And I get the RWD. You can also use it, use the same color as the before. So this is the relative water deficit. As I shown you before, you can use the raster layer statistics to compute the mean RWD value, which is 0.19. And yeah, and that's it from my side on a hands-on demo.
Thank you, Sajid. That was a explanation on how to calculate in QGIS the different performance indicators. So if you missed a few things or you would like to rewatch the video, remember you can always go to the WaterPIP project website or the waterchannel.tv and you can rewatch these videos again and again to make sure that you catch all the steps that Sajid just went through. So now we're going to move on to Bik Tran, who will talk about how to bulk download WaPOR data using Python.
Lauren. Hello, everyone. So as you can see from the presentation by Sajid and also from the demonstration using WaPOR portal, you see that using the WaPOR portal, there's no programming needed and it's very ready to use. The portal has very nice visualization. However, sometimes it's very easy to download a few raster files, but for example, if you want to download and to process a large amount of data, like for example, you want to process decadal data for 10 years, then with this WaPOR portal, it might take a lot of clicking and downloading data. That's why we want to use the WaPOR API because it's more time efficient to download large amount of data. It can also link with other programming language to automate processing and analyzing data by scripting. So just a brief introduction, what is the API? It stands for Application Programming Interface. So it's just a set of functions to communicate between the WaPOR database or the WaPOR service with other applications like web access or Python or any programming language. In order to connect with WaPOR, you need an API token. This is a unique identifier associated with your WaPOR account. So in order to get this token, you need to go to the website and choose My WaPOR. And in the profile section, you will find the button to generate API token. So this token is private and should not be shared with others. You can save it in a note on your laptop or somewhere. However, if you forget this, you can go back to the My WaPOR website to create a new one. So in this demonstration and also in ABB's demonstration, we will using the open source Python script that we developed for water productivity and assessment. You can access by clicking on this link here. You can directly click on this link, I guess. Then on the GitHub webpage, which is a web service to share all the open source code, not only in Python, but also in other programming language. In this webpage, you will find a button to clone or download. If you want to contribute or as a developer, you can clone it, or you can also just download the zip file so you can collect all the script in this repository. So in order to run the script that we will demonstrate today, you will need to install Python. We highly recommend that you using the Anaconda Python distribution. When you install Anaconda, you will also have Jupyter Notebook, which is a web-based application, including all the text and picture, also instruction, and the live code, either in Python or in R programming language. If you are using Python, you might have already installed some of these main Python package like NumPy or Pandas or GDAL for geospatial data analysis. In case you are new to Python, you can install these package by open the command prompt windows and using the pip install command with the name of the package, and then you can install this Python package. So once you have an active WaPOR API token and install all the Python requirements and download the open source script that we provided, you will be able to follow the steps in this bug download WaPOR with Python script demonstration. So now I would like to share my screen to show the demonstration. Okay. Abraham, please. Yeah. So is everyone seeing my screen yet? Okay. So now I hope you can see my screen at the moment. Lauren, can you check if everyone have seen it?
Yes,
okay,
we can see
thank
it.
you. So this is the GitHub page, as I've showed you before. You can click on this clone and download and to download the zip file. And then once you download it and extract the zip file, you'll get this folder called WaPOR WP. And in this folder, you can go directly to the notebooks folder. Here are all the steps of this demonstration. If you install Python or Anaconda distribution, you can start Jupyter Notebook directly from the folder. And then here you can start Jupyter Notebook from here. So in this folder, you will find the 6 notebooks from step 0 to 5. And here I will demonstrate how to bulk download data from step 0. So you click on this notebook, and then it will open a new tab. For some of you who have never used Jupyter Notebook, there's something you must first to know is this is where you check the status of Python kernel. If it's the circle like this, which means it's now at rest, so there's no code running. In this notebook, you will find some cell with the code and some cell with text explanation. So in this notebook, WaPOR data needed for water productivity assessment will be downloaded in bulk and corrected to the right unit. So in this notebook, we will download 6 data sets, actual evapotranspiration and interception, transpiration, net primary production, land cover classification, precipitation, and reference evapotranspiration. So all of this data, except for land cover classification, will be decadal temporal resolution, and the time coverage will be from 2009 to 2019. So as you can see here, it's more than 360 raster per variable. So it's a lot of data, and that's why we need to use the Python script. So here you will find the cell with the code inside. In order to run the cell, you will need to click run, or you can also press Control-Shift. This is to import some of the modules in Python in order to run the script. I will first click run here. And then the WaPOR module that we provide will ask you to provide the API token. Here I have my API token. I can copy this and paste it here. And then during that, the Python script will loading the catalog information from WaPOR server. You will only have to provide API token once because the script will automatically save your token in this folder. If you need to revoke a new API token to create a new one, then you have to delete this file called WaPOR API Token. So just to remind you of the steps to get the API token, you need to go to My WaPOR, and in this session you will see the button to generate API token. And you just have to copy this code. So now you see the number of the cell is 1, which means the cell has finished running, and also the status of the Python kernel is idle. Then next step, we will run this to read the shapefile of the study area. So in this example, I also provide a shapefile of Sinavan, the same with Sajid. So this code here to run and to read the extent. So here you will extract the longitude and latitude limit of the shapefile. You can also run this cell to plot the shapefile. And in order to bulk download WaPOR data for the study area extent, first we need to define the output directory. Here I put the path to the folder that I want to save data. And then I click run. So here we have provide the script in form of modules so that you can easily just use one function to download the data that you need. Here you only the land cover classification yearly. You only have to provide the arguments for start date, end date, and the extent of latitude in latitude and longitude. You can also select which level you want to download and which WaPOR version you want to download. So here, if I run the script, as you can see here, the status of the kernel is busy. So now it start downloading, and during this process, it will also correct for the unit conversion of the WaPOR data. So in the end, you will have all the data in the right unit. If you want to stop the kernel, you can also click here in the kernel and choose interrupt or restart or shut down. And then the same thing for other data sets. You can also just click run and everything will be automatically downloaded in, for example, here I save the data in this data folder. So here's all the data has been downloaded and corrected for the unit. For example, precipitation in decadal data. Yeah.
Thanks, Vic. Is that the end of your tutorial? Very nice. So I think, as you can see, if you will be downloading a lot of these layers from the WaPOR portal, it would be really time-saving to be able to use Python to do bulk downloading. So again, if you missed some details, feel free to rewatch the video and follow all the steps that Vic just presented in her presentation. So now we will be joined by Abebe Chikala, and he will talk about assessing water productivity and other irrigation performance indicators.
So my presentation will be on assessing water productivity and other irrigation performance indicator using Python script. In fact, this is a follow-up from the previous two webinars. In the first one, we introduced the concept, and the second one also we showed what kind of indicators we could derive from the WaPOR dataset. And in this one, we'll try to answer how we could calculate those indicators. So this, of course, will be built up on the download data, as Vic already explained. As Vic already explained, then we will show the first step, which is pre-analyzing the data. As some of the layers are coming in larger or coarser resolutions, so they need resampling. For instance, reference evapotranspiration or precipitation, they need to be resampled or scaled down to the scale that fits the highest resolution WaPOR data we have, either level 1, 2, 3, that is 250 meter, 100 meter, or 30 meter, depending on what we have on the ground. And then again, the other thing we could do as part of the pre-analysis is masking out crop or non-crop areas. And as part of step 3, then once we have those corrected and prepared data, we calculate the seasonal water consumption or production. Consumption related to potential, actual, or just the productive evaporation or the transpiration. And as part of step 4, we calculate the seasonal, so based on the seasonal water consumption, then we calculate the irrigation performance indicators that include water consumption, beneficial fraction, equity, adequacy, relative water deficit, and reliability. And as fourth step, we calculated productivity. So the productivity includes both land and water. And as part of fifth step, then we try to identify the productivity targets. So the productivity targets, as we defined before, they are values compared across all the space in the project area, and which are in the highest percentile. And in fact, we defined when only both water productivity as well as biomass are the highest, then that place or spot is identified as bright spots. And then as part of, again, the fifth step, we try to identify where exactly that bright spot is located within or across the project area. In fact, we did this systematically. So starting from downloading up to the whole analysis, and then, as already Vic explained, we developed a standard protocol for those analyses. And those protocols can be downloaded in our GitHub repository, which is wateraccounting/WaPOR WP. And it's freely available. And I'm going to walk you through that, how you could go from step 1 up to step 5. And I will share now my second screen, which will show that in the Python script. So do you see, I hope you see my screen, right?
Yeah.
Thank you. Okay, so the link is already explained, shown in our previous presentation. It's wateraccounting/WaPOR WP. In this link, you get all the scripts and also the data. And in fact, if you want to use this one, there is a nice, precise explanation, which is in the README file, how to go or what are the definition, and also how to go through each steps. And in fact, what let's say package to download and install, and also even how to install them is already explained here, and also by my colleague Vic in her presentation. So now, let's say once you have this one, then you need to download this, and then you can work on that one. So now I'm going to show you how, because once I already have the downloaded one here, then how will you do the analysis? So if you click, then after downloading, this is what you are going to find. So you have the data. So these are the data. The shape file are around here in this folder. And then the reference, actual ET, and transpiration and net primary production, those are the download data, which are named or started with 1. But the others are with 2 and 3 are going to be calculated, and I will show you how we will calculate. So the notes or then the scripts are in the notebook. In the notebook, then you could open Jupyter Notebook either through the command book prompts or directly if you type Jupyter Notebook, then still Jupyter Notebook can open for you here. So then we have this Jupyter Notebook. This already explained by Vic. Then I will start from the first step. So the first step is about resampling. As I said, there are 2 activities that we will undertake in this step. So the first one is resampling and masking out non-crop season. And as it's already explained, we need to import either standard libraries or modules that we already wrote. So there is a module that is adopted by our group, and then this is from where we are downloading, but then the others are standard library, and then we need to import them. So I first import that, and again I import all the data to be resampled. So my data to be resampled in this case is just to reference evapotranspiration. So I will then import it, and then these are the data. And then I create or I indicate the folder where I want to save that resample the data. So here I gave a folder name, this one, 1L, 1RET, then indicator 1. So yeah, whether we created or whether we have that folder also we can see it. For instance, in my folder, in the directory of C, then I will get it in the folder of WaPOR, WP, data, and this one. And then the resampling needs to start. It may take some time, that's why you see here the start, and also a dark spots at this point. So when it's finished, it becomes white. So at this stage, we can see, for instance, the size of and the shape of the resample data. So the size and the shape of the resample data is now 151 row and 250 columns, or the total file name is this much, it's about 37,000. And the second step is, in fact, filtering non-cropped area. So there is a land classification map in WaPOR, and this is how the numbers in the class are how they are classified. And the ID indicates, for instance, 42 is cropped or irrigated land. So in my case, I want to do only the analysis for the cropped land. Then I will filter out all the rest and then retain only the pixels which have a land class 42. So this is first importing the data. So the template data, I need to use a template data with which I can do the filtering. So for instance, I want to filter out from the actual evapotranspiration data. And then if I plot just the whole boundary of my project area, this is how it looks like. But then before removing or filtering out the non-cropped data, the actual evapotranspiration look like this one. So it's beyond the project area. Even in the project area, there are spots where there is no irrigation, or which are settlements, for instance, in this area, but they are there. So I want to filter out those, and that's then the step I did in my previous, and then here I could show you in the picture also. So this one is, in fact, after filtering out then the irrigated, the non-irrigated area. So you see that now all non-irrigated area are removed, but still there are areas which are part of the analysis. And again, I want to remove all of them which are outside my scheme, because my scheme is somewhere, it looks like this one. So anything outside this and even in between should be removed. So in this step, then that's what I'm doing. Then this code does that. So this is the first step. And the second step, once we have a clean data, is about analyzing. So the analysis will be, in our case, the second step, the step to be analyzed in this case is the seasonal water consumption and production. That includes seasonal actual evapotranspiration, seasonal transpiration, seasonal reference evapotranspiration, and seasonal net primary production. It's already shown by my colleague using QGIS by Sajid, but now I will do the same, not for one season, but for multiple seasons, just with a click, just using the script we have here. So the first thing is importing the libraries. The libraries functions which help me to calculate, and the second, or to analyze. And the second step is again importing all the data which I want to do the analysis of. And in this case, I need to communicate with the WaPOR, because when I let's say when I add the rasters, then the script needs to identify if the rasters fall within that crop season or not. When we download from the WaPOR database, there is already around it, so by its name. So the name, for instance, here is level 2, actual evapotranspiration, and 2009, and the first decade, which is T5. Then for that reason, I need to communicate with the WaPOR API, the modules that Vicky explained. But in this case, and always if you use this script, I will recommend you only to run this once, because when you run it, then it saves already automatically in your computer with this name. And it is, in fact, saved here. In the data, all the names here are the saved one. So once you saved it, then the second time you need to just use or read from whatever you saved. And in this one, I will just read whatever I saved before. And then here, I will create a folder. So the folder where I want to save the seasonal transpiration, actual evapotranspiration, and net primary production are named with this folder name. So they are now created already. And this function, in fact, adds all the seasonal from the starting to harvesting. And for that, in fact, it uses planting date and harvesting date. And I will explain in a bit where you will edit your own planting and harvesting date. So the planting end, or the starting and end of the crop season, it's already in the Excel file. I saved it with SOS, EOS, which is starting of season and end of the season. And I will show you where I have it in my folder. In the folder, in the data, at the end, you see here the seasonal starting and ending of the crop season. If you open this Excel file, of course, you can edit the planting. Well, I should just open it. Okay, well, until it opens, then I can continue. So those planting and harvesting dates, then if I run it, then it reads from the Excel file. So it means I will use those planting seasons. That is from 1st of October up to end of September. That is along all the years from 2009 up to 2018-19. Then we start to calculate the seasonal. For instance, the seasonal transpiration, if we click, then it saves it in a folder because we are giving the folder where it has to be saved, and also it plots it here. And similarly, we can calculate the seasonal evapotranspiration. That is just for the whole season. So you might see here it's busy because it's calculating and it adds the graph. And then just within a click, we have a seasonal actual evapotranspiration of the whole 10 years. And similarly, for reference evapotranspiration, the same can be done. And the final seasonal for crop production is the seasonal parameter I want to calculate is the net primary production. And then again, this can be just calculated through the same, just clicking. And of course, you can do the same. I mean, that is also the idea of you can use or modify this script to calculate the seasonal water consumption and evaporation. So the third step is calculating the performance indicators. So the performance indicators in this case are water consumption, beneficial fraction, equity, adequacy, relative water deficit, and reliability. And you could read about those. In fact, they were already explained in our previous 2 webinars, but still you could use some of those references, and also from the README file that I show you from our GitHub repository, what they mean, and also how they are calculated, all the equations. And again, we start to import all the equations, the functions, the standard libraries in the Python. And then, of course, the first one is calculating the equity. So equity is explained as a coefficient of variation of the actual evapotranspiration across the whole area. And then if we want to calculate, then it can be also saved. These are the values. So for each, when I printed, so for each season, 2009/2010, these are the coefficient of variations for different years. And in fact, if they are fair or poor, those indicators are also mentioned here. And again, as I said, from the reference, you could check what I mean by fair, uniform, or not. And the third things to calculate among the indicator is the beneficial fraction. Again, for this one, we need input of transpiration layer and evapotranspiration layer, which are the actual and across the whole season. First, we read and we import those files. And in fact, if we want to see whether we import them or not, this is actual evapotranspiration, and this is the transpiration. If I run it, then I can see, yes, I'm downloading 10 season transpiration and 10 season actual evapotranspiration. And then first I specify the output folder where I want to save. Then in this case, I named it 3 beneficial fraction. So that is the folder where I want to save it. And then if I run it, then it means this is the folder and it is created. And if I want to know whether it's created or not and where I have it, then I just can run also after including this name. Then it will be in the data with the name 3 beneficial fraction. So then I will calculate again the seasonal beneficial fractions, and then I can save it also in the folder. So if I run this one, you see the beneficial fraction maps for the 10 seasons. The other parameter is, or indicator is actual adequacy. It's calculated with this formula, which is actual ETA, seasonal over seasonal potential evapotranspiration. And the seasonal evapotranspiration, as explained by my colleague Sajid, is average KC, that is the weighted average, times the reference evapotranspiration from the season. So since we are talking about seasonal layer, then this has to be averaged over the season. As you could see here from the graph, the KC varies along the crop stage. So initial development and the mid-season, late season. So we weighted based on the value, magnitude of KC, as well as duration of each stage, crop stage. So I think this formula explains. So to do that, then after calculating for sugarcane, we got 1.045. And also we need to import the other parameter, which is actual ET and reference evapotranspiration. And then again, similarly, I will specify or create a folder where I want to save the adequacy. That is what is being done at this step. And then finally, I can calculate and then I can plot. I will show you how the calculation is done. So in fact, the whole script here is just import and then do the calculation and then save it in the folder and also name it with the name adequacy. So if I run this one, then we start to generate the map at the same time saving the whole folder, the whole layers in the folder. And in fact, we can also plot this along the time, just averaging one value per area. And then I can show you here, in fact, this script is doing that. So the adequacy for each season, and of course comparing with the good performance acceptance range and poor performance are again plotted. And the other indicators I have in this step is, in this step 3, is calculating relative water deficit, which is 1 minus actual evapotranspiration seasonal over the maximum evapotranspiration seasonal. Again, I import the input data which I need to calculate this, and then using this script, then we can calculate automatically. It's very quick. So with this, I will go to the fourth step where I would calculate the productivity. That is another indicator. So we have productivity, that's the biomass productivity, and also biomass water productivity and the yield. So in this case, if I use harvest index, then I can talk about crop yield. Otherwise, without harvest index, I'm going to talk the biomass. So the biomass over the actual evapotranspiration is defined as biomass water productivity. So again, I start importing libraries which I need to calculate those indicators, and also input data or layers to calculate the biomass or the crop yield. So that is the net primary production. So I collected from this folder. And then again, I create a folder where to save those layers or those analysis. Now I have the biome 4 L2 biomass. Of course, you can give your own name. It doesn't matter. So it means this is the way to calculate it. The biomass is, we have the net primary production, the seasonal one. First, we need to transform it into the dry biomass by multiplying by 22.22. And then from the dry biomass into the fresh biomass by dividing or correcting by moisture content, and then multiplied with a factor. For instance, if the crop is C3 or C4 crop. And in our case, sugarcane is C4 crops, then we use a value 1.8, which is to transform a light use efficiency, which is used in the NAPP, in the net primary production calculation in WaPOR, which is for C3, into the C4 crops. And then finally, we multiplied with above ground to the total biomass ratio. So these inputs are needed. Then if you want to run this script for another crops, you need to change those crop parameters. For instance, for sugarcane, we have a value of 0.8 or 8% of the total biomass will be above total biomass. And as I said, this is 1.8 for C4 crops, and for C3 crops, it's just 1 because the whole layer NPP in WaPOR is calculated assuming it is CC crops. That's why we just use 1 if it is wheat, for instance. But for C4 crops, then we need to change those parameters. And we have a moisture content. For instance, this is a value we got from an experiment one of our students did as part of his MSc in sugarcane production in Wanji. So we have this, we just use that value, 0.59. And the harvest index, we use 1 if we wanted to talk about biomass. But if we want to talk about harvest, a marketable yield, then we have to change this into the appropriate harvest index. And maybe in our repository, we will add some of those parameters for other crops. So we need to import those parameters because I want to calculate for sugarcane, and then I can calculate the biomass for sugarcane. So now you see it's being calculated and saved in the folder that I created. And similarly, we can import and calculate the water productivity. This script does that one. So I can just quickly run because it doesn't take much time. Once you have the script, then it means at the end you have the water productivity map. So my final step to explain is how we could identify the bright spots, and also how we could calculate the target, productivity target, and also identify bright spots. And also finally, if we want to calculate a productivity gap, how we could do that one. So again, I will start just importing the modules and the libraries which I need to calculate, and then I also import all the input data which are needed for that. It's actual evapotranspiration, biomass, and biomass water productivity. And then I will calculate the target productivity. The target productivity is defined as 95 percentile of the productivity. So it means for biomass, 95 percentile of the biomass across the space will be the target biomass. And similarly for the biomass water productivity. So I could use this function to calculate the target. It means now it's already calculated. Then the target value can be calculated like this. So targets impact biomass and target water productivity are this one. And also if I plot just for one season, it look like water productivity in the y-axis and then the biomass in the x-axis, and then this one will be the target one. So this is for one season. But then, I mean, this is also the distribution functions. And then when we talk about this point, it is around this value. But then all points beyond this one can be identified as a bright spot. And this function will do that one. It will try to find exactly where this bright spot or this spot will be located in our geographical area, project area. So it's now for each season where the biomass is greater than 95 percentile are the green areas, where the water productivity are greater than 95 percentile are again scattered with the red one, and the combination or the intersection of the two are now shown in the spot. So those are areas which have higher biomass and higher biomass water productivity. And in fact, we can trace across all the seasons, and also we can identify which location is really a bright spot, and from where we could learn the management, the smart management, which is going there, can be replicated for other areas. And then, okay, if we identify these targets, we can also calculate the gap. That is the productivity gap by comparing what is the target and also what is the actual per each pixel. Then the last function is doing that one. So first we calculate first we create the folder where we want to save the productivity gap, and then the biomass gap can be calculated while being saved in the folder, and then it can be calculated. So this map shows for 10 seasons what are the biomass gap, and then similarly for water productivity gap. This is biomass water productivity. So with this one, I'm close to finish, just only showing you now where are those results in the folder. So it means now you could see I have already those folders, 2, 3. If I open them now, I have 10 seasons where everything is calculated. So feel free to use this free GitHub. I mean this script, and come to us if you have a question. Thank you very much.
Thanks, Abebe. That was a really nice and thorough overview of how to use that Jupyter Notebook to go through all the different steps for calculating the performance indicators. So it sounds like you need a little bit of familiarity with Python and Jupyter Notebooks, but you can still make it work and work it for your own areas, which is really nice. So just as a side comment, if people are new to Python or GIS, there is a course, a free course from IHE that I'll put the link in the chat that goes over the basics of Python and QGIS. So if you're new and you would like to really use this Jupyter Notebook, but this looks very confusing to you, that course would be a really nice place to start. So I put that link in the chat, and I'll also put it on the WaterPIP website if people are interested. So I would like to thank all of our presenters. Really appreciate all of your knowledge and your live demonstrations. And now we will move on to the Q&A session. So the first question is for Bebe. It looks like multiple questions. So first, did you use AETI or ETA for the seasonal actual evapotranspiration? And then why is there no download product for ETA? And if you used AETI, does that mean we have to consider the interception in our calculations? Maybe you can address those.
Thank you. I think this is an interesting question. In fact, when we download the data from WaPOR, you might have seen the naming for evapotranspiration or actual evapotranspiration AETI, which includes evaporation, transpiration, and interception. And that is just decadal. And when I transform it into seasonal, I just name it ETA. That's actual evapotranspiration, still including evaporation from the soil, also transpiration, which is through stomata, and also evaporation from the canopy, which is named transpiration. So indeed, then it includes all those 3 components.
Bebe, for BIC, can I add any additional data to the layers I choose and save it to
Yes, I was also confused about the question. Maybe Rania can explain a bit more. If it's about the portal, sure, you can add additional data to the portal to show 2 or 3 layers at the same time. I hope it answers the questions, because I'm not really, I don't really understand the question, sorry.
That's okay. If she would like to post a clarification, please put it in the chat. But we'll go on to the next question. Nice presentation, Sajid. It will be complex for multi-cropping. And I think there were a few other comments about multi-cropping scenarios using this tool. So maybe someone can address the...
Yeah, thank you. Yes, it will be complex for multi-cropping. It will be complex from a temporal and spatial point of view. So you really need to understand what is the crop calendar and prepare system accordingly. So for example, one scheme where we know that it's pretty homogeneous, it's sugarcane, its season is from October to September next year. Okay, it's for that scheme we can standardize all these steps. So that is what Abebe has done with this Python library, which is available in GitHub. So for each scheme, you may have to do according to the local cropping calendar. Process-wise, yes, that is why we showed two aspects. One is using QGIS. You saw that okay, we have to manually choose all the layers and do it year by year. At the same time, Abebe using the Python script was able to do all the years in one go. But of course, there is a curve of developing that scripts. But that GitHub, which is openly available, could be a good starting point to extend it to another area. Can you use this in small scale multi-crop areas common in Africa? If you meant small areas as in spatially, so as you may know, WaPOR has 3 levels of data. First level is 250 meter, which is available for entire Africa and Near East countries. But I don't think that will be suitable for small scale multi-crop areas. And the second level is 100 meters. So all the analysis which we showed today was done on 100 meter level 2 data sets. So scheme of this size reasonably can be done, can be processed using level 2 data. But if your area is smaller than what we showed today, we have, for selected areas, we have level 3 data which is available in 30 meters. But it's not available for entire Africa. So if you go to the WaPOR website, you can see which all areas 30 meter data is available. I think it is on the way. It will take some more time to.
Thanks, Ajit, for that clarification. Another question, how do you validate your results versus observed data?
Abebe, in the Sinavana case, you want to answer this? I think we had some data from this.
Yeah, I can. Yeah. In fact, yeah, for validation, it's very crucial to have observed data on the ground. So if we are referring to evapotranspiration or transpiration data, then of course we need to have observed one if possible. I haven't done, or we haven't done that one specifically for this one, but of course we have done this in another publications. Which is a quality analysis, and you could refer to those documents. Maybe you could put those links big in the chat box. So there are already some analysis and comparison in that case. But for this specific Sinavana case, we compared with the FPO statistics reported data for SIGETCHEM, but then the value we got is average over the whole Mozambique, and it means including rain-fed, irrigated. Yeah, but then it looks like very reasonable in that case. And the other thing is we try to compare also conceptually. For instance, and in our previous in our second webinar, our colleague Pulad Karimi already showed, for instance, how the KY value, the yield response developed, in fact, not necessarily for this area, but for Bekaa Valley, for instance, fit the theoretical one. And similarly, we try to also explain, for instance, if we draw the averaged water productivity, the normalized one, whether it speak C4 crops, also then that is also another conceptual validation we did. So yeah, then in terms of yield for specific to Sinavana, we did a comparison, and it's more or less it's within the observed or reported in FPO statistics.
Thanks, Bebe. That was a really detailed answer. And okay, moving on to the next question. Can we
I think this question
or
might
open
need
2 layers
using QGIS. And in QGIS, you can open even more than 2 layers. However, I think there's not yet an option to put 2 layers beside each other. So you can overlay one layer on top of another.
And then visually you can see the differences. Thanks, Vic. Sajid? Oh, here he's back. You took the KC value as 1.0.
Yeah, I think Abebe in his presentation has already explained how the KC, we came up with the KC value of 1.045. You're right, it's over the entire whole growth period, and also it's based upon some experimentation study which one of our students has conducted in the area. So you're right.
Thanks. And then
I see Marvelous already answered that.
Does the WaPOR tool take
no,
into
water
account the
quality
quality
is,
of water that is?
I think we have to thank our colleague Marluz. She is answering or through the chat box. Indeed, yes, it's only water quantity and only production-related things are in WaPOR, not related to water quality. Nothing is, we don't have data water quality related layers in the WaPOR.
Thanks. And a question from Benjamin. How much time would it take to program a user-friendly front end for this tool? So instead of going through the Jupyter notebook.
I think it depends. It depends on the skill of the developer. But if you are interested and willing to learn, then I highly recommend to start with looking at the source code from our script. So it's open source. You can look at all the script from the modules to see how we're scripting out all of these Python code to use WaPOR API. So based on that, if you understand the WaPOR API in general, you can start scripting your own tool. I hope this answered the question.
And if people are interested in collaborating, please contact us if that's a project you would like to work on. Next question: are there any light or offline?
Yeah, I mean, go ahead, Vic. Yeah.
Yeah. So the good thing about WaPOR is that it has very high resolution compared to other remote sensing products, like 100 meter, and you see like 30 meters. It's very high for ET products. So if we have light version, then we have to reduce a lot of the quality, the resolution of the data. You can have offline if you download the data, but of course, to get the data, you have to have internet access. Sajid, do you want to add something?
No, I mean, you covered. The best way is to download the data whenever you have access to good internet, and then do all the processing offline. So whatever indicators and what productivity assessment which Abebe has shown is being done offline. So only the data download part was online. You need internet only for that.
No, this question from Abraham. How long will it take to download all WaPOR data? The question is, the answer is, it so depends. It depends on the internet connection, the speed of your internet. Normally, if I want to, for example, download the data for the 100 meter resolution of monthly data for 10 years, for example, Niger Basin, the area is about 2 million square kilometer, I guess. Then it will take like a few hours with my script, up to 3 hours. So yeah, it will take a lot of time because of the high resolution, and also depends on the area that you want to download.
So yeah, big. Then I think you said 3 hours, right? It's a very large, big river basin. Maybe I can put it also in the context of Sinavana. For instance, if I want to download only one layer, then it will take not more than 1 hour, in fact. And of course, if you want to download one layer by one layer time separately, it might take a lot, but still you can run the script in parallel and you could download all at the same time. It means in 1 hour, you could have the whole. So that is, in fact, based on the connection I have here. It might take a bit longer for other area, of course, or less or faster, depending on.
So if you want to download raster data, it will be fine if you need to download raster data. But if you only want to extract some time series, I recommend that you use the portal instead of download the raster and extract the time series from the rasters. Because if you use the portal with the analysis tool that I've shown in the previous webinar, all the processing will be done on the web portal, then you can just download a very light file of CSV file with all the data for the point or the area of your interest.
It seems like there's different ways to work around the issue of internet speed. One more question. We know that satellite-based data sets work poorly for the African conditions. So how sure are we in using?
Yeah, again, it depends. Well, in general, in Africa, we have smallholder farmers. Then if those sizes, the smallholder farmer size, if they are too small, than even smaller than, for instance, 1 pixel size, it's very difficult because a pixel covers not only the size of one farmer, but also even the neighboring farm or maybe the farm boundaries or other crops and so on. It's very difficult. Again, it depends. For instance, maybe if we are talking about the water consumption, for instance, still reasonably we might speak. But if it is crop specific, like yield or biomass, indeed it's difficult. But yeah, again, we have also in the WaPOR the finest resolution, which is 30 meter, and in some older farmers, again, it's even less than 30 meter by 30 meter. Again, it could be difficult. But again, what I would say is whether it works or not. For instance, if the smallholder farmer is still a bit larger in extent, it's possible to calculate and then to compare with the reality on the ground and then to speak. Otherwise, just judging only without doing anything would be difficult. And also some of the things which are happening now on the ground are also becoming smallholder, but again, even larger in a sense. For instance, in Ethiopia, I know there is a cluster farming. It means some couple of farmers together, they crop the same crops, for instance, wheat. And it means you have wheat almost everywhere in one neighborhood. So it means you can just do the calculation. Yeah, that's what I could say.
Great. I think that's our last question for the webinar. We only have a few minutes left. So I would like to say if this is, we'll be moving on to different topics. So if you have more questions about WaPOR, please feel free to go to the portal and look at the documentation that is there. But IHE is also working on an open course.
So we are developing an online course focusing on the water accounting and water productivity using WaPOR. So the course will have 3 modules. The first module will cover how to use WaPOR, how to download using QGIS, also Python programming. And the second module will focus on water productivity assessment. And the third will be about water accounting. So at the moment, the course is not ready yet, but if you are interested in the course and you want to join, please, after this webinar, you will see the feedback form. You can provide us with your email, and then once the course is online, we can share with you the link. So I hope if you are interested, you can join with us.
And yes, thank you. Again, the survey really helps us figure out who we're engaging with and how to improve these webinars in the future. And you can also sign up for mailing lists for the project. You can keep in touch and have the latest news on everything that's going on. So with that, I would like to thank the presenters. Thank you very much for your presentations and your input. And I would like to thank Abraham in the background for making this all work so smoothly, and also all of you who participated today and were so